So class is starting, and we ought to start going through the material. Let me go back to the place we started from, or where we stopped. It was somewhere near here. It was after here. Well, that's funny. I had it written in red. Oh, we stopped here. I actually added an extra section, an extra example, which I call your attention to. Not actually this section, this example, which I did mention, but it's complex analog, which actually, in a funny sense, contains much of the linear algebra that's actually used in quantum mechanics. And it's namely that suppose we want to find the extreme values of a complex quadratic form, Z transpose AZ, A being an n by n matrix, subject to the condition that Z is a complex vector of unit length. Well, applying the Lagrange multiplier technique, Lagrange function is f minus lambda c, where lambda real, we get these complex equations as well as the equation c equals 1, and subtracting the complex conjugate of this from that, interchanging I and j, we find, since lambda is real, that the two equations are consistent only if the matrix A is Hermitian. And so it's only Hermitian matrices that have real extremal values of this form, this complex form. So this in fact contains the essence, and in fact, in a sense, more than the essence of the section on Hermitian matrices. Anyway, eigenvalues. So you notice that, well, of course, what I failed to say here is that when this is the case, then AZ is lambda Z. And those are these equations, AZ equals lambda Z. And this is the equivalent equation provided A is Hermitian. Okay, eigenvalues and eigenvectors. Linear operator maps if it maps a non-zero vector into a multiple of itself, then the vector U is an eigenvector with eigenvalue lambda. Notice lambda can be 0, so A can map a non-zero vector into 0, but if it maps the 0 vector into 0, it doesn't have any particular property. Every matrix maps the 0 vector into the 0 vector. Eigenvalues span invariant subspaces. I didn't color that, but it's worth noting. The eigenvalues of a square matrix, this is particularly important. If you write the eigenvalue equation with indices, or you just rewrite it as, write this right-hand side as lambda delta ij vk, then what you see here is that this is a statement that the columns, these things are coefficients that in general are non-zero, and or not all zero. And consequently, this statement is a statement saying that the columns of V are 0. And I'm sorry, that the columns, if the entries of V are not, if the VK are non-zero, then the columns of the matrix considered as vectors are linearly independent. And that's because the coefficients coefficients, which are the elements of an individual elements of an eigenvector are not all zero. I must say that when I was writing this up, I got a little bit confused, so I'm going to blow away that and go back to what the original form was. I actually introduced a mistake this afternoon. So what this is saying is that the columns of the matrix are linearly independent if and only if the determinant of the matrix A minus lambda A vanishes. And that's, of course, what we learned when we breezed over the section on determinants. And so a solution of the eigenvalue equation exists if and only if the determinant of A minus lambda I vanishes. The vanishing of that determinant is called the characteristic equation of the matrix. And so for an n by n matrix, it's a polynomial n matrix of the nth degree in the unknown eigenvalue lambda. The leading term is just the term on the diagonal here, in which you just keep the lambda terms, and so you get -1 to the n, lambda to the n. The term without any lambdas is just the determinant of A, and then there are all these intermediate terms involving the trace and so forth. These coefficients here, pk, are all basis independent. And for any non-singular matrix, what we have is P of lambda A is what's called the characteristic equation. And that then is, as we see from here, it's a polynomial of degree n. And as we'll see in the chapter on complex variables, any polynomial equation has n solutions of degree n, has n solutions in the complex plane. So there are always n eigenvalues, lambda 1 through lambda n. So for every root, there's you have an eigenvalue, and there's a non-zero vector whose components are the coefficients that make the n vectors sum to 0. And so every n by n matrix has n eigenvalues and n eigenvectors. The diagonal matrix that's just made out of the eigenvalues is called the canonical form of the matrix. And the matrix whose columns are the eigenvectors is called the modal matrix. And if the eigenvectors are linearly independent, the matrix V is non-singular, and it has an inverse. And then one can form V instead of having AV equals A diagonal V, we multiply, or V A diagonal, we multiply by V inverse, and we get what's called a similarity transformation that diagonalizes the matrix A. So basically, every n by n matrix has n eigenvectors and n eigenvalues. If they are linearly independent, then the matrix is non-singular and can be diagonalized by a matrix consisting of its eigenvalues. The determinant of every n by n matrix is the product of the eigenvalues. Now, these eigenvalues, these n roots of the characteristic equation, are normally all different, and when they are, the eigenvectors are linearly independent. That's basically a proof of that. And one also finds that if all the eigenvectors of an n by n square matrix have different eigenvalues, then they're linearly independent. If any k of the n eigenvalues of an n by n square matrix have different eigenvalues, then they are linearly independent. Maybe I should say they too are linearly independent. So basically, a simple eigenvalue is an eigenvalue that occurs only once in the characteristic equation. If it occurs several times, it's said to have multiplicity n, and an eigenvalue that has multiplicity n in the characteristic equation is associated with n eigenvectors, and it's said to be n-fold degenerate, an n-fold degenerate eigenvalue, or to have algebraic multiplicity n. The geometric multiplicity, though, is the number of linearly independent eigenvectors with that eigenvalue. And a matrix with n prime less than n for any eigenvalue n is defective. So basically, if you have a one-to-one match between the eigenvalues and the eigenvectors, the linearly independent eigenvectors, then you have well, I guess you have a nice matrix, but I'm afraid I've lost track of what I was going to say there. Anyway, a matrix that has an eigenvalue that occurs n times in the characteristic equation, but is only associated with n prime or fewer than n linearly independent eigenvectors is said to be a defective matrix. And so what the basic conclusion then is that an n by n matrix with fewer than n linearly independent eigenvectors is defective. And the conclusion of all these definitions and theorems is that every non-defective square matrix can be diagonalized by a similarity transformation. Here are examples of defective matrices, and you can see that these are not have a suspicious look to them. Let's put it that way. The chapter on harmonic oscillators and coherent states is worth reading and worth knowing about. Coherent states have gradually become important in the last 100 years. I think they were discovered probably in the 30s, 40s. Schwinger made use of them subsequently. And in the 60s, early 60s, Glauber, who had been Schwinger's student, made coherent states a basic technique, or used coherent states to develop his, develop the whole field of quantum optics. I think a great fraction of the work was done by Glauber. Anyhow, a matrix obeys its characteristic equation. Well, remember the characteristic equation is the equation determinant of the matrix minus lambda times the identity equals 0. If you substitute for lambda the matrix, that's an equation that every square matrix obeys. So it's quite a remarkable result. Here's some nice stuff about spin 1/2 matrices so that you should learn, and especially while you're studying spin 1/2 in the quantum course. Functions of matrices. Suppose you have a function that's a polynomial with a convergent power series, ck x to the k. Now, what you can do is you can, in principle, express f of a in terms of n functions of the coefficients like this. F of a equals f sub k a to the k. And these functions are functions of these coefficients in the characteristic equation. anyhow, in order to see how this works, I think it's worth seeing how this works. So just suppose that A is one of these nice matrices that's non-defective and square, so you can diagonalize it. And so you can write f of A as V, f of its diagonal form, V inverse, and f of its diagonal form is just the diagonal form of f of each of the eigenvectors, eigenvalues. And so you have that f on the matrix is this sum of these coefficients ak, and they're a raised to the power k, and that's a v a diagonal v inverse to the k. And now this v, maybe I should show this in explicitly. What you have here, you see, is if you have here something like v, let me use the same notation. And in fact, let me make this thing bigger. So let me shrink this and make this quite a bit bigger before switching over. And let me just see what the notation is. VAV inverse, right. Okay, so we would have something like VA, V inverse, VA, V inverse, VA, V inverse. And this V inverse is just one. So this is VA squared, V inverse, dot, dot, dot. And then you have VA, V inverse V, that'll be again V squared, V inverse, and so forth. And this would be, if there are only these terms, this would be VA to the fourth, V inverse. And so that's what happens over here. And so you can write, if you have a matrix A that's non-defective and square, f of A is V, f of A diagonal V inverse, or V up V on this matrix, V inverse, V being n by n, this being n by n, and this is f on the eigenvalues of A, f of A1 up to f of AN. So I'm going to skip these things, and these are all examples that you should study, especially the ones that are physical. Hermitian matrices. Well, this is stuff that we already, in a sense, have gone over in that example where I said, let's find the extremal value, of something of this form, KAK. I called it Z. And well, if we do it the standard, what we found was that A should be Hermitian and so forth. And the eigenvalues were sort of automatically real. Anyway, since A is square, we can use section 130. And so we have an n by n matrix with n eigenvectors and eigenvalues. All the eigenvalues are real. Well, you just take the adjoint, use the fact that the adjoint is the matrix itself, and then you take the inner product of those states, and what you get is AK or A star K. This is very much what happened in that example that I started today's class with. Does anybody know how to get this thing to stay off the main page that I'm sharing? It's really annoying. Anyhow, what we see here is that all the eigenvalues are real. And then since A dagger is equal to A, the matrix elements between two of its eigenvectors satisfy this equation. A star M is AM KM star, and that's K AM star, because A on M is A sub M. Then when we take the complex conjugate, it flips and A becomes A adjoint, but A is Hermitian, so this is A. Now this is A acting on K, so that's AK. So altogether, we get that AM star minus AK on MK equals 0. So the eigenvalues are real, so we get this equation, and this tells us then that the eigenvectors are orthogonal if the eigenvalues are different. And then the rest of this section is sort of a long, drawn-out section in which I discussed what about degeneracy? Well, if you have a degenerate, if you have more eigenvectors, several eigenvectors with the same eigenvalue, and they're linearly independent, then what you can do is choose them to be orthogonal, because you can make any set of linearly independent vectors orthogonal and orthonormal for that matter. Then the question goes, the question is, well, what about what orthonormal linear combination should you choose? And the answer is you should choose ones that make some physical sense. And are they all linearly independent? And in fact, what you can do is you can show that an n by n matrix always has n orthogonal matrix, orthogonal eigenvectors. And this is a little bit subtle, so I'm gonna skip it here. The argument has as one conclusion that the Hermitian matrices are automatically non-defective. And of course, as I said earlier, a matrix that's real and symmetric is automatically Hermitian, and a matrix that's imaginary and antisymmetric is automatically Hermitian. And you can add two Hermitian matrices and you get another Hermitian matrix. And if you take a linear combination of Hermitian matrices, as long as you use real coefficients, you get a Hermitian matrix. This is kind of interesting. Cartan's tetrads. They're just four vectors. Well, let's see. This is a little subtle. 4 eta is the metric of ordinary flat space. So let me try to write on this so I can show you what I'm saying. So what we say is eta is -1, 1, 1, 1 with zeros here. And G is the matrix then of space-time. Oh, I didn't show you this in detail, sorry. It's -1, 1, 1, 1. Some people use +1 and 3 minuses. I think that's perverse. G is the matrix of space-time. Normal matrices, well, the largest set of matrices that can be diagonalized by a unitary transformation is the set of normal matrices. These are square matrices that commute with their adjoints. And it includes Hermitian matrices and unitary matrices, and some other matrices. I think, I don't think it's limited to Hermitian and unitary. Anyway, a normal matrix can be diagonalized by a unitary transformation. That's the basic thing. And any two eigenvectors of a normal matrix with different eigenvalues are orthogonal. And every n by n normal matrix has n orthonormal eigenvectors. So the normal matrices are a natural generalization of the Hermitian matrices, which with almost as many good properties. Time evolution operator is obviously of this form. Two normal matrices are compatible if they commute, and then they can be simultaneously diagonalized. Here are some more examples which you should know about, read. And now we get to something that is probably the main theorem of linear algebra. In fact, one could say that almost all of linear algebra is a consequence of this, of the singular value decomposition. And what I like about this theorem or decomposition is that it is so very general. You start with an arbitrary matrix, any rectangular matrix. It can be a might as well make this. Can I make this lower? Or does it just get bigger? It just gets bigger. Well, anyway, this matrix A that we're going to be talking about can look like this, or it can look like this. It doesn't need to be square. And it's just an arbitrary complex matrix. Doesn't need to have any special properties at all. And so the statement is that every complex M by N rectangular matrix is the product of an M by M unitary matrix U, an M by N rectangular matrix sigma that is zero except on its main diagonal, on which the A's are non-negative singular values, and an N by N unitary matrix. So N by N unitary matrix B dagger. So it can be written as A is unitary, positive on this diagonal at least, and or non-negative on the diagonal, and the adjoint of a unitary operator. Or equivalently, it's the sum, L goes from 1 to the minimum of M and N of UIL, singular value L, V dagger sub LK. So notice that normally you'd have two sums. You'd have a sum over the intermediate index here and a sum over the different intermediate index there. But instead, we only have one intermediate index. And this is a key theorem. I probably should have written the key theorem. And so I'm going to maybe go through this in a little more detail. So suppose A is a linear operator that maps vectors in an n-dimensional vector space into vectors in an m-dimensional vector space. So it's mapping from V. Oh, I shouldn't have used, this is bad notation. So let me just figures. I shouldn't have used two uses of V for the adjoint there and V for a vector space. I should have called this SN and SM, I think. Well, no, that's all right. Well, I'm running out of letters. Anyway, each of the vector spaces, Vn and Vm, has infinitely many orthonormal bases, Aj and Vn and Bk and Vm. Labeled, I'm just labeling them by parameters A and B. But in each case, there are n of these and m of those. And again, n and m don't have to be equal, and either one can be the big one, a bigger one. Each pair of bases provides a resolution of the identity operator In for n and Im for Vm. And so we can write In as the outer products Aj with Aj, and Im of the outer products of Bk with Bk. Notice how Dirac's invention of the bra is so useful. And of course, he also invented the ket. But this is such a nice notation. And well, I obviously have a typo here. Let me maybe I can just make this let's. So, and let's write, good God, I don't know what happened to me writing this. Oh, I hope this is an exceptional page. And let's write the linear operator A in this form. So A is the identity operator for the space VM, and IN is the one for the space Vn. And so we write it like this. And so these are infinitely many different ways of writing the operator A. The singular value decomposition is simply a choice of two special bases. And the bases are the bases that make this matrix here diagonal and non-negative. And so express A in this form. And you see, you remember that any matrix that takes you from one basis to another, by the way, I sometimes use the word base for basis. I really need to get that straight. And if any of you has a really good suggestion, send me email or shout. Anyhow, you remember that any operator, a unitary operator takes you from one basis to another, one orthonormal basis to another orthonormal basis. And so implicit here are the unitary operators, because when you take the matrix elements of A with some standard basis, say N, then this turns into the unitary matrix that we called U, and this turns into the adjoint of the matrix, or it turns into the matrix we called V adjoint. So let me, in fact, write that. I don't want this there all. So in other words, let's see, what was I going to say? Right. In other words, if we take N, A, M, what we would get here would be this sum over J.
We can't see that, Professor.
Yeah, I'm sorry. N, AJ. Actually, I need to look at what I'm copying. So let me just do it like that. Actually, those were called BJs, weren't they? So let me rewrite this as a BJ. And then SJ. And then this was AJM. And so this is what we would call sum over J. And what did I call it originally here? U. Okay. So this would be called U, NJ, SJ, V dagger, MJ. Or do I have that wrong? Is that V dagger JM? VM. You know, I think this is probably right. Or, well, it depends on what we mean by V. So anyway, that's how these things work. And so basically, so to repeat, we can obviously, by choosing two bases or bases or basises, the B's and the A's, and we have infinitely many choices for each, we can write A in this way. The singular value decomposition is a special choice. in which the special choice of bases in which we simply get this form. And the way we make that choice is the A's are a special basis of the domain space. They're the normalized eigenstates of the Hermitian operator A dagger A. So we multiply this equation by A dagger. And what we have then is, well, actually, we don't multiply that. We just know that A dagger A is a Hermitian operator, so it has n orthonormal eigenvectors called HA, and they have eigenvalues EJ, and they're real. Okay, so then we take the inner product with AJ, and we get, of course, that AJ is non-negative, and then we define the singular values as a square root of these eigenvalues. So those are, so then so it's really very simple. We have two arbitrary bases. We choose the basis A, the A's, such that they're eigenvalues of A dagger A with real positive eigenvalues, with the singular values of the square roots of these eigenvalues. And the other basis, the BJ's, are just the image of the AJ's under the operator A divided by the eigenvalue SJ. And now if you substitute this into there, what you get is that, well, first of all, you can find the BJ's are automatically orthogonal, and the operator A then, or the matrix A, is written as a sum of the BJ's, the outer product of the BJ's and the AJ's, and their outer products weighted by the singular values, which are non-negative. So this is, I think, a really nice, theorem. And as I said, it's the key theorem in linear algebra. And so this is something to emphasize the most in this first chapter, this theorem and the derivation here of it, or some other derivation of it that you might invent. So to recapitulate, because it's so important, what we've got then is we can write the operator A by slapping it on the left and right with identity matrices, and the identity matrices are just sums of outer products of dyadics, and in other words, outer product of vectors, and vectors that form that represent the identity operator. And there are infinitely many ways of doing that. Then we choose this basis, the basis of the domain space, to be the eigenvectors of A dagger A. They have positive eigenvalues. The singular values are the square roots of the eigenvalues. And the B's are just the image of the A's under the matrix A. So A maps the eigenvectors of A dagger A into the B's, and then we scale them by dividing by SJ. And just to show you then how this would work is, altogether what we're saying here is that A is a sum of, oh God, I've once again, here, I'm going to move this off screen so that I can both see it and not block out things. So what we said here was that we wanted to write A as woo. A as BJ, SJ, AJ. And so the BJ's, we said, were A on AJ divided by SJ, and then they're multiplied by AJ, and we're summing over J, and there's an SJ here that I left out. The SJs cancel, so this is just sum over J, A, AJ, AJ. But this sum over, and so we can rewrite this then as A sum on J, AJ, AJ, which is just AI, which is just A, which is of course what we had over here. So that's how that works. And what you see is just by, it's a proof by construction. And the remarkable thing is the proof is extremely simple and the result is extraordinarily general. And this is just a wonderful theorem that you can kind of do anything with. You can see that when, let me go over here. You can see that in particular, if you have A then as a sum of AJ, SJ, BJ, then suppose A is Hermitian, so then it's equal to its adjoint, which is a sum of BJ, SJ star, AJ. And now, if these two things are to be equal, then, well, they'll certainly be equal if S is equal to SJ star, and if AJ, oh, wait a second, AJ is equal to BJ. And so that's the Hermitian case where A then is a sum AJ, SJ, well, we know that SJ was real and in fact positive. AJ, hold on, I've somehow got this. I have somehow said that given that it's equal to its adjoint, I'm getting, if AJ is equal to BJ, this turns out to be a positive matrix, not simply a Hermitian matrix. So I must have been inserting an extra space. So I guess I shouldn't go offline too rapidly without thinking a little more. Anyway, that's the singular value decomposition. And notice the sum here is over the minimum of M. If M is less than N, it's a sum over M values of J at most. And if N is the smaller one, then it's a sum over at most N SJs. But it could be fewer because the number of positive singular eigenvalues, I mean, the zero matrix, for example, has all the SJs equal to 0. So here, this is so important that maybe I should do a couple of examples to make a matrix from its singular values and eigenstates. So suppose the special bras look like this, and the special kets look like that, and the singular values are 3, 2, 1, then the matrix is 3 divided, the 1/2 here comes from normalizing this. That's funny, I'm a little puzzled as to how square root of 2 went to 2. Anyway, plus this, and that gives you that. So let me just say that I will check 450. I'm a little confused about the factors of. Oh, they both have square root of 2's. No. It's B1 has a square root of 2 and A1 has a square root of 2. B2 doesn't have a square root of 2, but A2 does. So this is the way it works. So this is okay. So here is another way of saying some of these. So you pick two bases for the two vector spaces, write them like this, and then you get this structure here, KK, BJ, SJ, AJ, LL. That this gives us SI, delta IJ, and this altogether is U sigma V dagger. Okay. Anyway, the vectors B and A are respectively the left and right singular vectors. That's what they're called. And let me see. I was going to say something else about the B's. The left singular vectors, the BJ's, are eigenvectors of AA dagger. So they play, whereas the AJ's are eigenvalues of A dagger A, the BJ's are eigenvectors of AA dagger, which is also Hermitian. Okay, I think I'm just wondering how much more of this, how many more examples I should do. All right, let's go through to the end of the chapter, and if we have time, I'll come back and do these examples because, as I said, I think that's quite important. There's something called the Moore-Penrose pseudo-inverse. Penrose, by the way, is a mathematician who's worked in physics, especially gravity. And notice that a matrix A has an inverse if and only if it's square and has a non-zero determinant. We can use the singular value decomposition to make the pseudo inverse of an arbitrary matrix. So this is an application of the singular value decomposition that's particularly amusing. So what you do is you take the singular value decomposition and you write the pseudo inverse A plus as V sigma plus U dagger, and sigma plus is the transpose of sigma with every non-zero entry replaced by its multiplicative inverse. These zeros you leave the way they are, but so you invert all the elements on the main diagonal. So in other words, if sigma is 3, 2, 1, then sigma, what did he call it? Sigma plus? Yeah, sigma plus is 1/3, 1/2, 1, 0. And and it's the transpose. So in fact, it looks like this. So let me get my Jiffy eraser here too. So it looks like this. So it looks like that. So this is the Moore-Penrose pseudo inverse, and it satisfies these relations. The pseudo inverse in between two A's just gives you an A, so it acts like an inverse. The pseudo inverse on both sides of an A gives you pseudo inverse. A plus adjoint is A plus, and A plus A adjoint is A plus A. So A plus and A plus A are both Hermitian, and it's the only matrix that does these things. So let's see that I urge you to read the rest of this, but I don't know if we need to go through it in absolute detail. Okay, tensor products and entanglement. Well, tensor product is a fancy name for something that normally students just absorb naturally. In other words, in the simplest case, for example, you have our vector R, and we have no trouble saying that this is X, Y, Z. So this is an example of a tensor product, or R and I guess theta phi, although I'm not sure one can separate the theta and the phi quite like that. Anyhow, it's the idea is that you've got a composite system, so particle in three-dimensional space, or a system of two spin 1/2 particles that could be in the state plus, whoops, hold on, plus, minus, or minus plus, or minus minus, or spin 1/2 state, where here you could write plus meaning 1, 0 and minus 0, 1. And so this is, you often put commas here. This refers to particle 1. This, oh, sorry, you didn't see that. So particle 1, particle 2, and so forth. Let me see if I can just squeeze this in so that it's minimally big. So in this case, the inner product of two states, well, if they're orthonormal, it's just a product of the two Kronecker deltas. And an arbitrary vector in the space then is a sum of over ik of these inner products, and or a sum over ik, all the basis vectors with this is the inner product. This means that this state means the particles in state I and in state K. State I with respect to one condition, and state K with respect to the other independent condition. And the inner product of this vector with another vector then is simply the sum over ik of phi star and psi. And vectors that are tensor products of vectors in the two spaces are said to be separable, but most states are not separable and said to be entangled. And because this is the general state is ik, and then you sum over the iks with arbitrary coefficients, and in fact coefficients that aren't products the way I wrote them here, but instead are are of the form, let us say, phi sub ik. So in other words, the general, I should have another equation here. So in other words, the general state here the general state here would be a sum over I and K, and I'll just call it SIK, I comma K. And so this is the general state. And instead, the tensor product state is a sum over IK of phi I psi K, say, IK. And the point is that SIK is has n squared numbers, whereas phi I has n and psi K has n. So this has 2n numbers. So as n grows larger, and one gets in to describe some system that's macroscopic, the vast majority of states are entangled. But always there are more entangled states than separable states. So separable is when you can write it in this very, very, very special way. Then you can make a matrix operating on this tensor product space, and one way is to make it a tensor product of the two matrices, and so you have W acting on this tensor product matrix acting on V turns it into Aij, Bj here, Bkl here, and that's the Wik element. And you can also have a tensor product operating in the same vector space, of course. And tensor product operators, of course, are very special. The general operator takes the basis ket JL into all the possible basis states IK with this coefficient. Example is the hydrogen atom, where the states are labeled by energy, angular momentum, and projection of angular momentum on the z-axis. This state here is separable, and the states sigma plus minus are, anyway, I don't know if we have time to go through all of this, so let me just skip past this. An example of entangled states are photons from pi0 decay and so forth. Here's something about density operators. A general quantum mechanical system is represented not by a state, but by a density operator. And a density operator is Hermitian, of unit trace, and positive, or at least non-negative, in that for all the average value of the density operator in any ket is non-negative. And this term positive is, does one really always want to say non-negative? I don't know. Anyway, if the state psi is normalized, then psi, rho psi is the non-negative probability the system is in that state. And the probability is real because the density matrix is Hermitian. And if K is any complete set of orthonormal states, the probability of the system in that state is the average value of the density operator in the state K, or trace rho KK, KK being the dyadic. And since trace of rho is 1, the sum of these probabilities is equal to 1. That's why the trace has to be 1. So there's the general density operator. And if you're composed of two systems, it looks like this. And what you can then do is talk about the reduced density matrix. So you can trace over the second system, say you trace over the K states. And when you do that, then what you've got left is just the AJ. But the matrix element is this trace over the K states, and similarly over here. The other reduced density matrix is trace over the I states, and you get then KL. I'm not sure the notation is the greatest here. Anyway, you can define an entanglement entropy for system N as the trace of the reduced density matrix. Well, the entropy of the reduced density matrix. And all right, so let's see, how much do we have left here and how much do we have? We have 14 minutes left, so that's a considerable amount of time, actually. Let me just see how much we have left. Not a great deal. All right, so I can slow down a little bit here. Classical entropy is an extensive quantity like volume, mass, and energy. The classical entropy of a composite system is the sum of the classical entropies of parts, but the quantum entropy is not necessarily extensive. The quantum entropy of an entangled system can be less than the sum of the entanglement entropies of its parts. The quantum entropy of each of the eigenstates, gamma gamma and E plus E minus of example 1.75 is 0. But the sum of the entangled entropies of their parts is 2k log 2 in both cases. Okay, so that's an example of how quantum entropy can be different. And there's a Schmidt decomposition. Suppose psi is an arbitrary vector in the tensor product spaces. Tensor product of the vector spaces B and C. An arbitrary matrix A has a singular value decomposition. In terms of it, the vector psi is, and here we're summing over I, L. So this is the standard singular value decomposition. And the state, we can rewrite it in this way, where this is ULI, I, and so forth. The states UL and V dagger L are orthonormal because those matrices are unitary. The outer product of a tensor product state is a pure state density operator. Well, any dyadic of two normalized states is a pure state density operator. Anyway, it looks like this. If you take the trace over complete sets of orthonormal states in B or C, you get reduced density operators. And they have the same eigenvalues, same von Neumann entropy, and the non-zero positive singular values, SL, are called Schmidt coefficients. The number of them is the Schmidt rank or Schmidt number of the state psi, and psi is entangled if and only if its Schmidt rank is greater than unity. And the density operators there that we just talked about earlier have Schmidt rank 2. Correlation functions. This is more general and therefore possibly more important. We can define two Schwartz inner products for a density operator. If F and G are two states, then the inner product defined this way. So remember when I talked about inner products, they have to satisfy 3 conditions, which immediately imply a 4th condition. And One way of doing that is to say the inner product of F with G is just F rho G. And if F is and G are the same, it's non-negative, and it satisfies the other conditions for Schwartz. I see, for Schwartz inner product. This is not a general inner product. And the second Schwartz inner product applies to operators A and B. So these are two Schwartz inner products. The first is that. The second one is an inner product of operators, and it's analogous. It's trace rho A dagger B, or the trace of B rho A dagger, or A dagger B rho. This inner product is non-negative when A equals B, and it obeys the other rules for Schwartz inner product. So these are two different Schwartz inner products that are constructed in terms of operators and states in and I think Glauber and Titulaire invented, yes, of course, those are the names. They are non-degenerate inner products and are not inner products in the strict sense, but they are Schwartz inner products. So they satisfy the Schwartz inequality. And if you apply them to the vector inner product, you get this rule, which is a property for density matrices. And if you apply it to the second inner product rule, you get this trace inequality. So those are powerful inequalities, and Glauber and Titulaire use them to get some results based on the correlations functions that Glauber introduced in 1963. This is the work for which he won the Nobel Prize, by the way, these 1963 papers. Anyway, the operator E that represents the ith, E sub I of X, the ith component of the electric field at a point X, is the Hermitian sum of the positive frequency part and its adjoint. So it looks like that. The first order correlation function is the trace of rho E minus E plus. So this E plus is the sum of the annihilation operators, and these are the sums of the creation operators, the operators that create photons. And in terms of the operator inner product, it is E plus comma, E plus I, E plus J. That's because E plus and E minus are adjoints of each other. Now, let me actually check to see whether they're, yeah, that's right, because in terms of the operator inner product, you see you take the adjoint of one of them, and so one of the E pluses turned into an E minus. So setting A equal to E plus and B equal to E plus of Y indices I and J, you find that first order correlation function is less than the ith element at X times the jth one at Y. And then interference fringes are sharpest when this inequality is saturated so that Jij is equal to this product, and that can occur only if the correlation function factorizes. And that's when G1 is E star E, and it factorizes in particular when the density operator is an outer product of coherent states. These are coherent states in each mode of the radiation field. The radiation field has two polarizations for each value of momentum. There are infinitely many momentum values. Although if you restrict yourself to a laser with mirrors, then you can have well, a discrete infinity of the vector space has infinitely many orthonormal eigenvectors, but it's a discrete infinity, whereas, and far smaller than the one for all of space-time. Anyway, the density operator is an outer product of coherent states, and these coherent states, you see, what is happening here in this equation is that E plus sub I of x on this state, alpha, this is a squiggle. Well, what is this E plus? This is a sum over all modes of something like e to the I kx, a of k, and polarization s. S just goes from 1 to 2. And then a polarization vector, E of k and s, acting on this state, alpha. But A of k and s on alpha is equal to alpha of k and s, the state alpha. Here, this squiggle alpha is the state, is the set of alpha 1, 1, alpha, well, that would be actually K1. So, I don't know how to fix this without bringing in the damned eraser. Okay, so K1, 1, K1, 2, alpha, K2, 1, alpha, K2, 2, dot, dot, dot. So it's all the possible combinations, and the coherent state is an eigenstate of the operator. This is the annihilation operator. I think I have too many n's there, so scratch an n. Since the coherent state is an eigenstate of A, this thing is equal to the sum over k and s, e to the I kx, alpha of k and s, E polarization vector k and s times this state alpha. And so this is what we call E plus of x. And then you see we have this extra index I. Well, this index I is the polarization index here. And so that's how all of this works. And so then the higher order correlation functions are defined this way. And if you're in a coherent state, this is bingo. This turns into just a product of E stars with E's. And that's quite nice. Now there's a concept here in the last minute, the rank of a matrix. This is just a definition, and the 4 definitions: the number of linearly independent rows, number of linearly independent columns, number of non-zero singular values, and the number of rows in its biggest square non-singular submatrix. Software. There's a linear algebra program called LAPACK. It has codes in Fortran and C++. And if you want real speed, you need to use Fortran or C. Apple's Xcode command -framework accelerate links the software into GNU executables. Basic linear software, BLAS, on which Laplace is based, is available here as Fortran programs, possibly as C programs. MATLAB does a lot of numerical problems. a free GNU version is available there. Well, I should say it's not really a GNU version of MATLAB. It's the best GNU can do to imitate MATLAB. Maple and Mathematica are good commercial programs. Mathematica is more mature because it was better. It made more money and could hire more people. Python and Scientific Python, Sage are free software, which are good to know. Especially Python. Python is of enormous range of applicability. It's not just physics and mathematics, but it's sociology, English, maybe not that broad, but it certainly is useful in all kinds of engineering. And then there's Maxima, which unfortunately was supported by the government for a while, but then I guess the people, either they lost their government contract or they retired, and it's kind of fallen into, it's just been neglected, which is a real tragedy because it's much better. It was much better than Mathematica when they both were being developed. And I imagine it still is better in many ways than Mathematica. And the reason is it's based on Lisp, whereas Mathematica is based on C. And Lisp was designed for symbolic manipulation, symbol manipulation, whereas C was just designed for everything. And Intel has some software that's available. What I forgot to mention to you is that Fortran and such things and C are available from GNU. So the GNU Software Foundation supplies and constantly updates C and Fortran, C++ as well. These are basically, this is basically the end of this chapter, and next week we'll do, I guess we'll do chapters 2 and 3 next week. 2 is very short, and I added a section to 2, so there's a new section in 2 that I might point out to you because it's relevant. The reason I added it was that I needed it to do some stuff in chapter 1. So this is the new section, and it's just stuff that many of you probably knew or could derive on your own, but it's stuff that I was never taught, and I just suddenly saw show up in various Russian books, and in fact, it's also, of course, used in books written in English or other ordinary languages. So let's see, does anybody want to write anything on the chat, or I don't see any chat comments here. I don't know if this means I'm going way too fast, or I can't be going too slow because I'm going maybe twice as fast as last year, so as to cover more material. Some students complained that in previous years, the course went too slowly, and especially I think for the linear algebra, because you guys knew most of the. Okay, well, thank you for those comments on chat. I will, the way to submit the homework is to send it by email to the grader or put it in the grader's box. Now, I am not entirely sure yet who the grader is. Maybe well, I hope to find out quite soon, within a week at most, who the grader is. And so at that point, I'll be able to tell you who it is and where to send the homework. At the moment, it's a little bit confused. I completely agree with the student who said that, or who chatted that the, or two students, one person said it was fast, another one said it was a lot to absorb, but, and that the student may have more questions when doing the homework. Let me, to comfort both of you, the material that you haven't, that may seem strange to you because you haven't seen it before, is probably less important than the material that is familiar to you. But on the other hand, there is one thing that you probably haven't seen that is very important. That's the singular value decomposition. As I said to you, the singular value decomposition is very simple, very natural. The proof is just very simple, and the proof is the theorem is incredibly general, and it's the most important theorem of linear algebra. By the way, I was once at a party in Santa Fe, and it's almost the only one of the very few parties in Santa Fe that I've been to. And at the party, the man who invented MATLAB, who used to be a professor at UNM in the computer science department, came up to me, and he's a big bear of a man who's not at all shy, and he said, I told him I had written a book, and he said, did you include the singular value decomposition? He was sure I hadn't. And I said, yes. And he was surprised and happy that I had, because he knew that in physics departments, the singular value decomposition is almost universally neglected, whereas people who really understand linear algebra know that it's the most important theorem of all linear algebra. I am going to try to be, weather permitting, to be on the campus. I tell you what, it'd be Saturday afternoon, Sunday afternoon, Monday afternoon. I can't do it Tuesday, Wednesday, Thursday because I teach, and then Friday is the physics colloquium. Let me say, what I'll do is I'll send out an email if I'm going to be on the campus on tomorrow, or any day that I'm going to be there. I'll send you an email. I don't want to make it, I don't want to freeze it now, but I think there'd be no harm to going there, let us say Sunday or Monday. Well, I don't know whether, how many prefer weekends and how many prefer weekdays? One person for weekends. All right, well, let's say I will tentatively aim at Sunday, but of course, you know, if it's raining, then we have to stay outdoors because of COVID, at least from my point of view. The other, anyway, so I'll aim at Sunday, and we'll just see what Sunday afternoon. I don't know, 4 or 5, something like that. I'll send you an email. When is too late for you guys? some of you eat dinner early possibly, or I think actually because everything here in this class is 5 or 5:30, I think I'm going to make it 5 or 5:30 just so we don't get confused with times. So I'll think about 5:30 this Sunday. Again, if it's clear. I don't know what the weather's supposed to be. I trust my iPhone to tell me these things, and I can't at the moment find my iPhone, so I can't tell. And the iPhone's open wrong. All right, well, I've talked too much. Why don't I let all you guys go? I'm going to stop recording.